So a two-dimensional version, the function that's a function of two variables, could be captured in a similar way. So let me redo this setup, but let us supply different inputs to F1 and F2. So for example, here's F1. It takes an input A and generates an F1 of A. And here's F2, and it takes an input B and generates an F2 of B. And we're going to take these and we're going to multiply them through some multiply. And what comes out is F1 of A times F2 of B, which we can think of as a composite function of two variables, where this function, which we call g of A comma B, is just F1 of A times F2 of B. And this is just multiplication, it's not composition in a functional sense, it's just plain multiply. So again, if we leave everything in D mode, this is taking the value of F1 of A, the value of F2 of B, and multiplying them and giving us the output. So what happens again when we put these cells into C mode, and we add a feedback again so we don't disturb. I don't need to keep showing that, but I will. And we take the output of this and load it into a cell that's also in C mode. So the question is, how will the function of this cell be programmed? And the answer is it'll be programmed like this new function F1 times F2, a function of two variables. Now to see that takes a little bit of hand waving, a little bit of imagination, but let's just look at this question of how do we code a function of two variables in some kind of truth table memory, right? A continuous or analog truth table. And go back to the idea and the implementation talk of maybe a deformable membrane. So we have a space of xy, and at each point xy, this membrane is deformed according to the function value at that point xy. So we can think of the storage of a cell's program as some sort of matrix. And it's going to move to having dimensions n by n, where n is growing towards infinity. But let's just do a simplified version. Let's just think of a range from 0 to 1, and let's just do this by tenths. And how could we store the value of a function of two variables? Well, let's just pin down a map here. And this is going to be f of 0, 0, this is f of 0, 0.1, f of 0, 0.2, all the way over to f of 0, 1. And then this next row is going to be f of 0.1, 0, f of 0.1, 0.1, f of 0.1, 0.2, all the way out to f of 0.1, 1. This is f of 0.2, 0, f of 0.2, 0.1, f of 0.2, 0.2, all the way out to f of 0.2, 1, and so on down to f of 1, 0, f of 1.1, f of 1.2, out to f of 1, 1. And so the idea is, in this matrix of 11 by 11, 121 values in this case, the value stored at each particular row column is f of row comma column, scaled, right, or non-integer rows. So this is row 0.2, this is column 1. So this is the function value at 0.2 comma 1. So basically we're just storing x and y, and what we store at any point is f of, in this case, y comma x, so row comma column. Details aren't important. The idea here is that we lay out the function values in this two-dimensional arrangement, and if we want to know the function value at some particular point xy, we can find a position in here and read the function value out. So that's the deformed membrane, for example. Alright, so this is what we have. So go back to our example circuit. We have f1 of A and f2 of B. These are both functions of one variable. So if we want to code f1 of A, and this cell is actually able to store a function of two variables, what would we do? Well, we could store the following. We could store f1 of 0, 0, f1 of 0.10, f1 of 0.20, all the way out to f1 of 1, 0. And we're going to store the same values in every single row, so that the value of this second index will not matter. In other words, it won't matter how far down we are in this membrane. It's basically storing a one-dimensional waveform. So this is f1 of 0, 0, f1 of 0.10, f1 of 0.20, f1 of 1, 0. And this goes all the way down to f1 of 0, 0, f1 of 0.10, f1 of 0.20, out to f1 of 1, 0. So the idea is we store f of column, comma, 0. Or let me put that differently. In a particular row and a particular column, the value that we store is f of the column number. So if you like, f of r comma c equals just whatever the function value is at c. We ignore the row basically. Okay, so this code's a function of one variable c, and c just says how far over do we move, what column do we look at to pick off the value of this function. Now f2, which was programmed from a different side, gets stored differently. f2 of b gets stored as follows. f2 of 0, 0. f2 of, let's see, so it's going to be row, comma, column. So this is next row. So f2 of 0.10, f2 of 0.20, all the way down to f2 of 1, 0. And then in the next column we store exactly the same information. f2 of 0, 0, f2 of 0.10, f2 of 0.20, all the way down to f2 of 1, 0. And we do this all the way across. And in the last column we store yet another copy of this single dimensional information. So what we have here is the entry at, let's just say the entry at a particular row and column is equal to, and it's just f2 of the row. So if you look in row x, you're going to find the value of f2 of x, no matter which column you look in, because everything is identical across the row. So by configuring f2 so that it calculates f2 of a different input side, for example, a might come in from one side, b might come in from a different side, we could have f2 laid out like this and f1 laid out like this. Now what happens when we put these cells in C mode is we begin to sweep through our cell in some kind of raster pattern, maybe something like this. And doing it like this, if your function is continuous, will ensure that your output has some sort of continuity condition, because we move across x and then we change y very slowly. So as we sweep through this pattern and we load values into a target cell in the same raster pattern, what is the value in our composite cell that we were creating by multiplying? Well, the first value that gets loaded in will be f1 of 0, 0 times f2 of 0, 0. That's f1, f2 of 0, 0. And the second value will be f1 of 0.1 times f2 of 0, that's f1, f2 of 0.10, all the way over to this, which has f1 of 1, and this, which has f2 of 0, this will be f1, f2 of 1, 0. And if you work through this on a bigger sheet of paper, what you'll find out is that at row, comma, column, what you've stored is f1 of row, sorry, f1 of column times f2 of row. Because at row, column, the value coming out of F1 will be F1 of C, and the value coming out of F2 will be F2 of R. And so we store this multiplicative product at each position in here, and the value stored in a particular row and column is given by that product of F1 and F2. So now when you take this composite block and you put it back into D mode, and you feed in two inputs, you're going to specify a row and column in this memory, and the value you're going to read out is based on F1 of one input and F2 of the other input multiplied together. And so again, we can take this circuit that has two functions, each one with an independent input variable, and creates a new cell which has a function of two input variables whose output is the product of F1 of A times F2 of B. So it's just an idea of how we can take the basic architecture of the songline processor, and by looking at the C mode behavior, start to do some manipulation of the functions themselves. Right? So we can not just multiply data values going into and coming out and manipulate them as numbers. We can start doing the same thing with functions. And we can actually treat the functions, the code if you like, of a circuit as just another analog value that we manipulate, we store, we transport around, we replicate, we modify, and ultimately we use to create a new cell whose behavior is given by that serialized coded function. So that's an idea that there's still a lot of work to do on, but the basic setup is there in the songline processor architecture, and it mimics the behavior of the cell matrix cells and their interchangeability between C and D mode, the non-dualism, all of that stuff is replicated here on the SLP using C mode. So that's an ongoing area of interest and research.